Hi, this is Amir Mehpana. I'm a PhD student at KTH Royal Institute of Technology. Today I'm going to present our paper that has been accepted to ICML. In this presentation, I'm going to quickly go over this agenda. First, I'm going to say what is explainability and why it matters. Then I'm going to say what is the research questions that we're focusing on in this work, and then what is the proposed solution that we have. Okay, so let's see, what do we mean by explainability? In old times, we had to solve our problems by hand. But nowadays, we use machine learning, which means assuming a functional form and optimizing the parameters. And because we solve our problems with optimization rather than analytical theory, we don't know how the function is reaching to a decision. Is it really reliable? Studies have shown that it is really not the case. Usually machine learning models can reach to a decision in very peculiar ways. To solve that problem, we have a new field emerging in AI, which is called explainable AI. And it tries to explain how a model is reaching to a decision. One of the ways that we can explain a model's decision is to use attribution methods, and that means we use heat maps on top of the input to show which features the network is sensitive to. But that description of attribution is deceivingly simplifying the reality. In practice, we observe that attributions change a lot in the vicinity of an image, and they can also change sign and be unreliable. So when we look at the previous solutions to instability of attribution methods, we realize that they can be grouped into two general approaches. One of those general ways to mitigate attribution instability is based on architectural modification. In fact, it can be shown that ReLU plays an important role in instability of attributions. In this work, we call them generally post-hoc or anti-hoc architectural regularization. Another, maybe more intuitive solution is to include the input curvature as an auxiliary term in your training loss. And based on how you compute this curvature, if it is adversarial or mean curvature, you can call it adversarial training regularization or explicit curvature regularization. Okay, now let's see what we have found. We use a body of established work that relate the input space curvature with parameter space curvature. Note that input space curvature is related to attribution robustness and parameter space curvature is related to training dynamics. Moreover, this is already established that if you use a larger learning rate closer to edge of stability, you can bias your optimization towards solutions that have lower curvature in parameter space. Now, if we use this connection between input space curvature and parameter space curvature, we can show this bias is not happening only in parameter space, but also we can bias the optimization towards solutions that show higher attribution robustness. Therefore, by highlighting the implicit effect of parameter curvature on attribution robustness, we are adding a new dimension to this problem. And this view brings new methods to our perspective, which are implicit curvature regularization and sharpness-aware minimization. In this visualization, we put methods on the boundary of a named region when they depend on it, and in the interior when they modify that. So to conclude our study, we can see both theoretically and empirically that training dynamics is playing a key role here. This is a new dimension to attribution robustness and deserves its own study. Moreover, we have seen empirically that we can bias the optimization towards solutions that we like, the ones that have higher attribution robustness. And this means maybe we can avoid training with costly input-dependent auxiliary losses and architectural modifications. Finally, I would like to add that we have done this study for vision transformers and realized that most of the techniques are developed for CNN and MLP class architectures, and they don't necessarily or trivially transfer to vision transformer architectures. Thank you very much for your attention.